Hello, everybody, and welcome to our latest Hubble Hangout. We are back from our 2-week summer break. Thank you guys for watching today. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really great hangout planned for you today. Today we have a hangout planned today. Okay, so I'm going to be redundant also. But today we're going to be talking about...
today?
What?
Sounds like you planned it today.
It's today. It's today.
No, I didn't. It's tomorrow. Okay.
All right, let's get into
today's topic is we are going to threw off my groove there. So today's topic, we're going to be talking about supernovae, what they are, the basics of them, and some of the latest research with supernova explosions. We have a panel of astronomers here to help us with that. Joining me this week, as they always do, is Dr. Carol Christian. She's from the Space Telescope Science Institute. Also, welcome, Carol. Did you have a good vacation? Did you have a good time off?
Absolutely.
Yeah. Okay. Also, is Scott Lewis from KnowTheCosmos.com, and he's all over the place in the internet, doing all kinds of awesome things. Welcome back, Scott. It's good to see you again.
Yes, good to see you too. Okay. I've missed you.
Yes, I've missed you too. Yeah.
I haven't missed you guys at all.
I've missed you, Carol.
Oh.
I don't care what you say. I've missed you.
Okay.
I just need to aim better. I'm getting rusty.
Okay.
So, like I said, today we are going to be talking about supernovae, and we want you to interact with us. And the way you can do that is Hubble Hangout hashtag on Twitter, the Q&A app on YouTube and Google Plus, and the Google Plus event page. We hope you'll leave us questions and comments. Also, we're noticing that there is a new thing on the Google Hangouts on Air interface. There's a little pair of hands where you can, I guess, do something, applaud or something like that. So feel free to use that and do whatever that thing does. I don't know what it is yet. We're going to be experimenting with this thing called a showcase, where we're going to try and show you some new things during the Hangout as well. All of that will be a little bit experimental. So let's get on with it. Supernovae explosions. That's what we're here to talk about today, and they are among some of the brightest events that occur in the universe. They are these deaths of stars that are, for a brief period of time, can outshine an entire galaxy. In fact, they will put out more energy in a few weeks and a few months than the sun will in its entire lifetime. So these are very energetic events. They occur at a rate which we will talk about a little bit later on. I don't want to give away too many punchlines because I just want to give some background on the kinds of things we're talking about. Not all stars blow up. Only certain ones do. There's also different types of stars that are explosions that can happen. And to talk about all of these details today, we have a panel of expert astronomers. And let me introduce them first. From Rutgers, an astronomer, Sarab, is it Ja?
Ja, yeah.
Oh, great. Oh, man, I love that when I don't screw it up too bad. He's an astronomer at Rutgers University. Also with us is Ryan Foley, a professor of astronomy at the University of Illinois, a place where I spent a couple of years, so it's nice to see somebody from U of I there. Also, Curtis McCulley, he's a postdoc at, you just say it. Where are you from, Curtis?
So I'm at LCOGT and UCSB. So LCOGT is Las Cumbres Global Telescope, and UCSB is University of California, Santa Barbara.
Okay. Thank you, and welcome to all three of you. So let me start with you, Sarab. Can you give us some background, some basics on what supernovae explosions are? What are they?
So that's great. And supernovae are exploding stars, so we have this word. And even the word sometimes trips people up. So we usually say one is a supernova with just an A at the end. And if you are talking about more than one, then that's supernovae with the AE. It's this funny Greek-Latin hybrid thing. So the New York Times calls them supernovas, so feel free to call them supernovas as well. That's totally fine.
No, supernovae.
No? We can't? Oh, okay.
Yeah.
Sorry, New York Times.
You have to say supernovae because it's fun.
All right. Yeah, so they're exploding stars, and as you said, right at the end of their lives, some stars explode, and I guess we'll get into which ones do. And there are many different kinds, and we're trying to figure out what kind of stars turn into what kind of explosions, and the Hubble Space Telescope has helped a lot with that.
Now, we know a lot about supernovae already. I mean, we've been seeing them for thousands of years. I think the first recorded supernova, as we're always taught in Astronomy 101, was in 1054, right?
Yeah, there may be some records even before that, but yeah, 1054, we have a pretty well-documented one, and you can go back and look at records that people kept in China and Japan saying in fact, on July 4th, 1054, before the fireworks still existed. Yeah, absolutely. But there were some celestial fireworks that day.
I don't think that's a plug for America, though. Just
America.
America.
It was a premonition of great things to come in America. Yeah, and then actually, what the amazing thing is now we can go back and the astronomers at that time kept really good records of where that new star occurred, and we can go back and look at that right now. And when we go there, we point, for instance, Hubble there. There are beautiful images of the Crab Nebula. So we can see now the guts.
Scott's got it up now.
That exploded in 1054. So almost 1,000 years later, we can see what it looks like. So it's pretty amazing.
And this would have been something people could have. Well, obviously they did look up and see it in their own night sky. And I believe they're saying it was bright enough to be seen during the day. Is that correct?
Yeah, I think that is true. Yeah, and it's in the constellation of Taurus, I think. And usually at that time, new stars in the skies, that was usually bad for the king or the emperor or whatever. That was usually a bad omen. But for us in astronomy, we love to see stars explode and see what they're made of, and see them enrich the universe with all that stuff.
Yeah, comets have that same reputation. So, all right. So supernova explosions are a way in which a star can die. Now, most people know. And if you don't, I'll remind you that stars burn through nuclear fusion. They have these gases that let them shine, and it's very complicated, and they generate a lot of energy. But stars also come in different shapes and sizes and colors and temperatures. What kind of stars end their life this way? Let me get Ryan in on this. How about, can you take that one for me? Oh, you're muted, I think.
Sorry.
There you go.
So first of all, what we think is just about every star that's particularly massive, say something that's 10 times as massive as our sun or even more, will probably explode as a supernova. There's some actually really interesting theoretical ideas that maybe some subset will collapse directly to a black hole and not have a supernova at the end of its life. But the vast majority should, and we've seen this because we've been able to detect stars after we've seen the explosion. We've gone back at our old images and seen the stars there, and then we see the supernova, and then we look much later and we see that the star is gone. So we know that that's happened. Then there are less massive stars that eventually, after going through this full process of living their lives, kind of like our sun, and going on to another stage called like the red giant stage, where they're really big and puffy, and then eventually becoming a white dwarf. A white dwarf is essentially just the center of that star after all of the nuclear fusion has happened, and it's just slowly cooling down. But a subset of white dwarfs that are in systems with another star very nearby can gain some mass from that other star and eventually get to conditions inside the star where you can restart nuclear fusion, but you restart it in a way where the nuclear reaction is a runaway. It causes a major explosion, and that will result in a supernova. So those are the two main categories of stellar explosions.
And the big factor here that determines whether a star explodes or not is its size. And I think you said 10 times the mass of our sun, right?
Yeah. So there's one of the very important areas of research right now is determining the exact minimum mass, the smallest a star can be and explode in that way. And most people kind of are pinning it around 8 times the mass of the sun. But 10, we will see that thing explode for the most part. But yeah, and it's actually the mass of the core near the end of its life, not necessarily how much how big the star is when it's more like the sun when it's burning hydrogen into helium. It's really at the end that matters. But that's a technicality. For the most part, we can if it starts off at 10 times, it'll explode.
Okay, so one thing I want to clarify is you said that there's two ways they can be triggered, and one of them had to do with the white dwarf being somehow reignited, or somehow fusion processes being restarted again, and then that exploded, right? So
Yeah.
is there two explosions then?
Well, no. So these are two separate events completely. So one are the very massive stars that they
They just blow
explode
up.
they blow up because eventually what ends up happening is that the fusion in the core of that star is no longer able to counteract the force of gravity, and so the star collapses in on itself, and that can cause an explosion. And it's the release, that, like, nearly instantaneous release of gravitational energy that's very it adds to that explosion.
Wow, that's cool.
For the white dwarf, on the other hand, if you slowly add material to it, it'll become more massive. And because it's more massive, and a white dwarf is a very funny object, it's called a degenerate object. We don't need to get into the details of it, but what it means is that the more massive it becomes, the smaller it actually gets. And so the density goes up a lot because you're making the mass higher and the size of it smaller. So as the density increases, eventually you get to a point where you have so many carbon atoms that are really close together that the carbon will fuse together. And when that happens, when you take a carbon atom and a carbon atom and you fuse them together, that's nuclear fusion. It releases energy. And the conditions of the white dwarf are such that once you start that process, it becomes a runaway, and it'll burn through the entire star. And that explosion is what we call a supernova as well.
So you describe white dwarfs as degenerate stars, and I love that because anytime we can use that word in astronomy, it makes me laugh. But where did the white dwarf come from to be able to have that happen?
Right. So again, the white dwarf is sort of the end of life for most stars. The star like our sun, after it burns all the hydrogen into helium, and then it goes through this other phase where it'll burn the helium that it generates now into heavier elements like carbon and oxygen. Eventually, because it's not so massive, it can't continue to burn heavier and heavier elements, and it just stops. And the core of that star, after that fusion has essentially stopped, is then the white dwarf. And a white dwarf is about the size of the Earth. It's not huge, but much bigger than the size.
Right. So you see my confusion, though. You said that's what's going to happen to our sun.
Yes. But our sun will never explode.
Eight solar masses or greater. So how can a star that big get do they make white dwarfs too? I mean,
yeah. So if you're above 10 solar masses, you'll never get to a white dwarf because you'll have a supernova before that can happen.
Okay. So this subset that we're talking about, this white dwarf supernova,
yes,
is nowhere near as common.
So
he's not telling you part of the story.
He's
not telling you about the companion.
I told you about the companion.
Well, we didn't hear it. So
Okay.
you have to say again. So we're envisioning this white dwarf like the sun, except it's not like the sun.
No, the
because
sun will
there is
never
no
explode.
there is no companion. That's where the extra stuff comes from.
Yeah. So the sun will never explode, and most white dwarfs will never explode. Only a small subset that have companions, and the conditions have to be right so that you can transfer some of the material from the companion to the white dwarf in the right way. And if you do everything just right, then you get a supernova.
Okay, good. There we go.
So,
I just wanted to make that. Okay, Scott, I don't know if you have it handy, but there was a graphic of that, I think, sent by Curtis, pointing that, just sort of an artist rendition of what that looks like. But if you can't find it, that's okay.
Yeah, let me get that up real quick.
Yeah, okay.
But in terms of how common each of these each of these types of supernovae are, they're roughly the same. Although the kind from more massive stars are slightly more common in terms of how often they occur, but just because of the characteristics of the explosions, the white dwarf supernovae tend to be brighter, and so we find more of them generally.
Okay, but just because they're brighter.
Yeah.
Okay. So before we leave this topic, and while we're on that, we've mentioned our own sun a couple of times. Curtis, let me get you into the conversation a little bit. Let me ask you. Ryan's already told us that our sun's not going to blow up. What will it do?
So at the end of its life, it's going to transition from burning hydrogen and it's going to start burning helium in the core, and it's going to, as Ryan mentioned before, it's going to puff up into a red giant. And kind of at the end of all of this cycle, it's going to blow off the outer layers, kind of puff off the outer layers, so not really an explosion, but something a little gentler. And it's going to create something that looks like a nebula, and what's going to be left is a carbon and oxygen white dwarf.
Okay, so Scott, you had it up briefly. Can you show it one more time? I'm going to put this up while Curtis is to illustrate his point. So, our sun, when it dies, will leave behind a white dwarf star. This won't be what happens in our particular case, but some white dwarfs have a companion, a nearby star, from which it can draw material. And here's the cartoon showing that now that Scott has up. And you can see there's a much bigger star surrounding and orbiting in unison with a slower white dwarf. These things are very dense, as Ryan pointed out. It's one of those things you hear in high school all the time. 1 tablespoonful of this stuff will weigh bajillions of tons, and your mind is like, okay, that's a lot, that's a big number. But suffice it to say, these are dense objects, and here's a cartoon of what Ryan was talking about. So for a supernova like this to occur, Ryan, it has to gather enough matter or mass from this other star to reignite fusion within the degenerate star, right?
Yeah, that's correct. In fact, the picture that you're showing is a very particular and very, very interesting, especially for the people on this call, type of supernova. And so you're absolutely right. It's the same kind of thing that we've talked about, but this specific example, and I'm sure we'll get into this eventually, we think that although you'll have a runaway nuclear reaction that will cause an explosion, the star itself may survive.
Oh, cool. Okay.
So I have a question.
Carol, you didn't raise your hand.
Oh, sorry. One question. I don't think I have to raise my hand, but
no, you don't. I was just kidding.
So I know you're going to talk about how you determine in detail using Hubble and other observatories. But the first question is, we know they get bright, so somebody discovers it. Maybe even somebody at Las Cumbres discovers a supernova, and then how do you know right off the bat what type of supernova is before you decide to start investigating it in great detail and maybe looking at its see if it has a binary star or whatever? So how do we know the type? What makes it a type?
Yeah, so there are a bunch of different types of these supernovae, and there's sort of 2 ways that we like to classify them. One is like trying to understand what kind of system was it. Was it a massive star, like the first kind that Ryan mentioned, or was it one of these white dwarf supernovae? And so that's like a physical kind of type. What was the system that exploded? Unfortunately, we don't usually get to see the system.
Right.
We're not there, so we don't get to see it. We just get to see the light from the system. So what we really get is we usually go and take a spectrum. So we take that light, we spread it out into its colors. With Hubble, for instance, we can do that, especially in the ultraviolet and other parts of the spectrum. But usually we can also do it just from the ground-based telescopes in the visible. And then we look for what elements are in that spectrum, and that gives us a hint as to which of these kinds of supernovae they are, what kind of star it came from. Actually, for a long time, so people have been doing this for decades. And like in the 50s and 60s, people would see these new stars, these exploded stars. They would get a spectrum, and they would say, oh, it looks like it has hydrogen in it. We're going to call that a type 2. And here's one that doesn't have hydrogen. We're going to call that a type 1. And they didn't know what kind of stars were necessarily responsible for those 2 different types. So they just kind of classified them based on what the spectrum was. And we still do that today. So we have all these different types. The type 1 that later got subdivided into type 1A, 1B, 1C, and then type 2s. And then there are even some other types that, in fact, some of us, especially Ryan, have helped coin. And the big goal, actually, in supernova research is to connect the type of supernova we see from the data, from the spectrum that we measure, to what kind of star was it? Was it one of these massive stars that are on the screen now? It turns out that we think the type 2s and the 1Bs and 1Cs come from this kind of massive star configuration, whereas the white dwarf supernovae mostly account for the type 1As. But that was actually only knowledge that was sort of gained through observation and modeling of these supernovae together to kind of come together to a consistent picture, but it's still the forefront of research, connecting the data to what actually exploded.
And you have to catch them pretty quick, right? I mean, you have to, so there are searches to try to find the supernovae and then immediately start observing them because you want to catch them as close as you can to when they blew up. Is that right?
That's right. Yeah. I mean, the earlier you can see them, you can see different parts of the supernova. Actually, as time goes on, you usually can see deeper and deeper into the supernova. So you learn about the structure. So in that massive star diagram where you have that kind of onion skin structure, you can see different elements in different layers of the star as you look deeper. But one of the important reasons to try and study them when you first go off is because they're usually not too much. They may take a couple weeks to get to their peak brightness, but after that it's all downhill. So you want to study them when they're bright, when we can collect the most light from them and learn the most about them.
Okay, so also Curtis, you had a diagram of the different types. Can you put that back up, please? So
Sure.
there are. Well, let's talk about all the different types that there are, and let's just go into detail about them now. We know that we get them quickly. And we'll talk about the way they're discovered in a minute. But we have here, according to what Curtis is showing, a type 1A, type 1B, 1Z, and a type 2. Who wants to go through some of these? Well, like type 1A, they're very special kind of supernovae. They're really useful in a lot of ways. Ryan, can you tell us about these?
Yeah,
Type
absolutely. Type 1A.
Type 1A are the best, by the way.
Yeah. Second best now. No, so type 1A. I wrote my PhD thesis on type 1A supernovae. There's always a special place in my heart for them. And they are exceptionally important objects for understanding the universe as a whole, which, if you think about this tiny star somewhere in some distant galaxy exploding, and that's supposed to tell us about the entirety of the universe, that's important. So the type 1A, if you're looking at Curtis's little diagram, he's got this very nice final line that distinguishes from the type, which is based on the observations, with our physical interpretation. And so the type 1A is this thermonuclear explosion. This is what we think is coming from a white dwarf that explodes. It has a thermonuclear explosion that will completely shred this star, and as a result, generate a bunch of radioactive material, in particular radioactive nickel. And that radioactive nickel decays first to cobalt and then to iron, which is stable. And in that process, the energy that's released on timescales of days, weeks, months is injected into the material that the supernova ejected outward. That's the shredded star. And then that material glows, and that's what we see as the supernova. Now, this type of supernova, because of some of the intrinsic properties of the explosion and the star system that they come from, they all seem to be about the same intrinsic brightness. And so we call them standard candles. And in much the same way that you can, when you're driving at night on the highway and you see distant lights from a car, you can estimate how far away that car is by noticing how bright the headlights appear to you. Since you know roughly how bright a headlight should be, you can estimate how far away it is. We do the same thing for supernovae. We have some idea of how intrinsically bright they are. We measure how bright they appear here. And so from those two measurements, we can estimate the distance. And
that's a huge point. I really want to make sure people understand this, because imagine taking a candle, folks, right next to your face. It's going to have a certain brightness. You're going to feel the heat from it. And don't burn your hair, but it's going to have a certain brightness. You measure that brightness of what it is right by your face, and you move it and put it across the room. It's going to be dimmer. How much dimmer it is will be related to its distance. And the only way you can know how far away it is you know how bright it is far away, is knowing how bright it would be if it were right in front of your face. And knowing that, and that's is an important element in measuring how far away things are, and that's why type 1A supernova are so useful.
Right. So in addition to that, it's that all of these candles we don't get the opportunity to move the candle close to us and see how intrinsically bright it is.
Right.
But we know that the candle store makes all the same brightness candles, and so the supernova store also happens to make all the same type 1a supernova brightnesses, or about that.
Oh, Curtis has a great graphic up while you're talking. Go ahead.
Oh, great. And so so from that we can measure distances, and because type 1a supernovae are also, in addition to being these standard candles, they're also very, very luminous. They're intrinsically bright. We can see them very far away, billions of light years away. And from that ability to find things on the other edge of the universe, and then compare how bright they are to how much the universe has expanded in the time between when that supernova explosion happened, because remember, billions of light years away means that it happened billions of years ago. And so you can compare those to the amount that the universe has expanded during that time to its distance, and that expansion history, right? Because it's a you're looking back in time. That expansion history is very much dependent on the exact content of the universe, and this ability to measure these distances and compare them to the expansion, to get the expansion history, led to an assessment of what the universe was made out of. And about 15 years ago now, or not quite 20 years ago now, two groups of astronomers used observations of type 1a supernovae, and they made this assessment. They went through and they said, something's kind of funny here. It looks like there's some sort of anti-gravity in the universe, and they went back and looked at some of the notes from Einstein, and he had this idea of something called a cosmological constant, which produced sort of a cosmic anti-gravity, and the observations appeared to be that the universe actually had a very large component of something that we now call dark energy, and that's essentially just showing our ignorance. We don't really know what it is, and that's actually the majority of the universe. It's somewhere around 70% of the universe is this dark energy, and we just figured that out, less than 2 decades ago.
And type 1a supernovae, as you pointed out, were instrumental in that, and it was done by two separate groups. In fact, Carol and I, Carol, we gotta do a dark energy hangout at some point and talk about some of this stuff.
Well, and so it's really worth pointing out that that Hubble was instrumental in this as well.
Yes.
And Sarab should really be giving this, because Sarab was on one of these teams that made this discovery.
Do you have any comments you want to add to that?
Have you been holding out on us, Rob?
He's been polite.
It was a very exciting time, let's put it that way.
Yeah.
Figuring out the universe was, I mean, it's really strange because it's, using these white dwarf stars that we don't, when they explode, and we don't really understand how, and I guess we'll get into that a little bit, but we use them still. We saw that they're basically all the same, so we can measure these distances. And we found that the universe, the galaxies in the universe, we knew they were expanding away from each other, but that they were expanding away faster and faster, that we lived in an accelerating universe. That was a huge discovery. It's like if you threw something up in the air, and instead of it coming back down, or instead of it slowing down as it went up, it just started going faster and faster. I mean, and so we call that wide dark energy, but Ryan was exactly right that that's just a name for our ignorance. And so it's that discovery that started from these type 1a supernovae is now at the forefront of cosmology, trying to understand what this dark energy is that drives our accelerating universe.
Well, you raised an interesting point, and actually Ryan mentioned as well, is that we can't bring those candles to us. And so from the signature, the observations, you say, oh, this seems like it's a type 1a, this one seems like a type 1a, and then you said, well, maybe we don't fully understand how this explosion occurs. Does that make you nervous? I mean, how much do we not know that they're all the same?
Yeah, it does make us nervous, and in fact, my PhD thesis was all trying to show that how similar are they, and trying to figure out a way. We know that actually there's some variation in how bright these type 1As are, but we can use clues from the light from the supernova itself to correct their brightnesses, to make them even more standard. So sometimes we call them standardizable candles or calibrated candles. So yeah, we do have some ways of checking that. For instance, sometimes we have two type 1a supernovae that went off in the same galaxy, And so we can check that do they end up being the same brightness because they're the same distance away. Or more generally, two Type 1a supernovae at the same redshift. Or when we know one should be twice as far away as the other because it has twice the redshift nearby, then we know that that one should be 4 times fainter because it was twice as far away. So we can check all those things without knowing anything about the explosion, really. And when we do those checks, we see how precise they are, and they're remarkably precise. We can with a good light curve of a Type 1a supernova, we can measure its distance to about 10% accuracy, or maybe even a little bit better.
So the light curve is how bright it gets, and then what happens after it starts to fade.
That's right. It's a trace of how bright it is over time, and it usually takes weeks to months to brighten and then fade away. Yeah.
Okay. While we're on the topic of Type 1a supernovae, I have a question from Bahez Ahmed from. In a Type 1a supernova, what happens to the companion star? Who wants to take that? Can you hear me?
Yes.
I mean, I guess I can mention this. So the good question first, before you ask what happened to the companion star, is to understand what the companion star is. And so for Type 1a supernovae, we have 2 very, very different scenarios, and depending on those 2 scenarios, then it really changes what happens to that companion star. So I'll try to generalize this, but if I get into jargon, somebody stop me. The one way is if you have 2 white dwarfs that slowly come together. There's something called gravitational radiation, and so these orbits slowly come together, and then eventually they merge. Another possibility is that you have a white dwarf and then something more like our sun or a red giant that slowly transfers mass onto the white dwarf. So in that first scenario where you have 2 white dwarfs coming together and they merge, then that other star is gone. It's become part of this massive white dwarf for an instant as the explosion just goes through it. So in that case, it's completely gone, just like the star the primary, more massive star that explodes. In the other case, where there's something more like our sun or a big star, it's a little unclear exactly what happens. There was this giant explosion right nearby, and so something must happen. We have an understanding of that, and there have been a lot of theoretical modeling to try to figure this out, and so there are a bunch of things that we know will happen. So the supernova shock from that explosion will go through and eventually hit that star, and some of the material from the supernova will be deposited into that star, and the combination of those 2 things will potentially change how bright the star gets, and some other aspects of it. But the other thing that is very important is that you used to have these 2 stars in a tight system where they were going around each other, right? They were just orbiting each other, and then all of a sudden one is gone. And so what happens to the other one? This is like if you're holding hands with somebody spinning in a circle and you let go, right? You just fly off. And so in this case, when you have these 2 stars going around each other, one just explodes, the other star is just going to fly off into space at essentially the velocity of the orbital speed. So so those are sort of the basics that we know. We don't think, for instance, that the second star will explode. That doesn't seem to be the case, or something like that. The actual changes to the star are probably minor, but some models have actually said that they could change in a way that it would be observable.
Okay.
So
now I actually have a question about that though too, because we were talking about earlier about the supernova 1054 and the Crab Nebula, and a few months back I did a show about the Crab Nebula, and we can actually see the pulsar inside of it. Can we go into a little bit of the pulsar? So here's a graphic I made. from observations from Hubble and Chandra, so we can see them in the different wavelengths of what's been observed over the years and seeing these ripples through this pulsar wind. Can we go into a little bit of that with the supernovae?
Sure. So the Crab Nebula one, because we see a pulsar there, and a pulsar is just this very rapidly spinning neutron star. So even more dense than a white dwarf. We talked about white dwarfs that were roughly the size of the Earth. A neutron star is like 10 kilometers wide, so the size of a kind of a big city. So you imagine taking like solar masses worth of material and really compressing them in to nuclear densities, and you get a neutron star. So in the kind of supernovae that come from the massive stars, that's what can be left behind. The core collapses all the way down to either a neutron star, like in the Crab Nebula case, or a black hole. And so there's some systems where we might think that there's a black hole there, not a pulsar. And so that's what gets left behind. The core of the star that actually exploded is that neutron star. So it's pretty wild.
Okay, Curtis. So this is let's go back to the different types real quick. Let's finish that up. Curtis, could you put that back up? That one
Sure.
one type of graphic you had. So that's type 1. We've covered that one. There are other types, and these were characterized by core collapse supernovae. First of all, what's a core collapse supernova? Curtis, can you take that one?
Sure. So the core collapse supernovae come from these massive stars. So as Ryan was mentioning before, the high mass stars will explode because the core will no longer be able to sustain fusion, and eventually it'll collapse under gravity's the gravitational energy. And that's what's being put back into the ejecta. So the core collapse supernovae are aptly named in as much that their core collapses, and then the outer material, the outer envelope, hits that inner core and bounces off, and it explodes as a supernova. And so that pulsar, like we were talking about earlier, is what's left behind. That neutron star is what's left behind. It's the core that of the star that exploded.
So the one that produced the Crab Nebula was a core collapse supernova then?
Yes.
Okay. So, and these can be kind of all over the place as far as brightness, right? There's no way to really, I mean, they're all varied brightnesses depending on what? How big they are? How massive they are?
On a variety of things. So everything from how big they are, if they have a binary companion, just like the white dwarfs. Even massive stars can have binary companions, and that can drastically affect their evolution. Or how much their winds might have actually blown off the outer layers of the material can also affect things. And so there's a lot of different variables in these core collapse supernovae.
Awesome. Okay, so
yeah, it's really, I mean, we're using kind of like normal words to describe these really amazing things, but every once in a while I like to remind myself we're talking about the core of this massive star right before it is about to collapse is almost like a white dwarf at that point. It's a few solar masses of material the size of the Earth, so that's already mind-boggling. And then in a millisecond, it collapses down to 10 kilometers.
Oh, I know.
It releases all that energy, and the rest of the star gets blown apart. I mean, this is why we like to study these things. It's just
I know. Astronomy's full of that kind of stuff, though, isn't it? I mean, we get so flippant about certain things. Oh, yeah, 100 billion stars in a galaxy, 100 billion galaxies in the universe. Yeah, you just sort of say things, and it's just when you really stop to think about what this means, it can really be quite humbling. Scott, what are you showing?
This is another one of the graphics I made for that show where the neutron star there, it's the mass of 1.4 suns in a 20-kilometer diameter.
Yeah.
And it's all of, and it's going to be a little hard to see here in the Hangout because it is a really quick image, so I'm going to be putting it into the event page and tweeting it out here in a second. But it's really crazy to think about, a 20-kilometer diameter, but the same, it's more massive than our sun, almost 1.5 of the masses of our sun in that small volume.
That'll fit in the Beltway, won't it, Carol?
Some days you wish it would fit in the Beltway.
Yeah,
all that traffic.
Yeah. Would like all that stuff to fall into it, actually.
Yeah, we could put that thing inside 695.
Take care of the traffic.
Yeah,
the cars orbiting it would go
out here
pretty
too.
close to the speed of light, so that'll speed up your commute pretty.
Yeah.
Oh, that'll God, we sure need that.
Yeah, but then there's spaghettification that might be happening too.
We don't need to talk.
Okay, so I want to cover a couple more basics on supernova. Then I want to talk into some specific Hubble observations. So we know that that supernovae are they have different types or different brightnesses. How often do these things occur? How common is a supernova explosion? How often okay, let me simplify the question. In our galaxy, the Milky Way, how many times will we see an explosion like this?
You just made it harder.
Oh, I made it harder?
Yeah,
so
by
simpler, right? Okay, in the universe.
Yeah, that's easy.
So,
how often do these occur?
So the number I remember is in the visible universe, there's one every second. In our galaxy, there's roughly one every century. Off, but that doesn't mean that we see them all. Because of just our location in the galaxy, we're in the disk of the galaxy. Most of the stars are in the disk as well, and there's a lot of dust in the disk. And so most of the time we're looking through that dust. That dust makes it hard to see other things. And so most of the time we won't see one. So the last supernova that has definitively been seen by people on Earth from our Milky Way was over 400 years ago. To give an idea.
It was observed by Kepler in 1604. Yeah.
And so even though
so we're due.
Well, you could say that, but then there was a very nearby supernova in 1987 that occurred in a dwarf galaxy that orbits the Milky Way. So it's right in our backyard, and so that happened.
No, it doesn't count. It's got to be in the galaxy.
It depends on how you do your accounting.
Yeah.
That doesn't count. Ryan's because. I mean, imagine 1604, that was when Kepler observed his supernova. Actually, just 32 years before, in 1572, there was another Milky Way supernova. And so the people who lived then, if they had the Hubble Space Telescope, they would have learned all this amazing stuff about those.
They bogarted all the
30 years in our galaxy.
Yeah, okay.
Yeah.
Well,
okay,
still, I want to stick up a little bit for 1987A because we have lots of HST observations of it. We've actually been able to see it change over time, which has given us some interesting information about super surroundings.
And honestly, from my perspective, I would rather see something in Andromeda than in the Milky Way, because in the Milky Way, odds are it will be in the disk. It will have a lot of problems actually figuring out what's going on, whereas Andromeda, the next big galaxy, it's one of those things where you can probably make very precise measurements of it, and it's still close enough where you can get all this extra data that we're really hoping to get.
How about the SST?
It's a funny irony, actually, because we have big telescopes and they're expensive instruments, but obviously I think totally worth it because of all this stuff that we learn about them. So we put our best instruments, our best cameras, our best spectrographs on those biggest telescopes. And if we had a supernova like the star Betelgeuse, for example, it's due to explode any time in the next 100,000.
We couldn't do anything about it.
It would be so bright. We wouldn't be able to use any of our great telescopes. It would be too bright for those telescopes.
That's right.
And we'd all have to break out our celestrons and our, our binoculars and our eyeballs and try and learn that way. So.
Well, I'm glad you brought that up. I'm glad you brought that up because my next question, before I start going to some other comments, is: are we in danger? Is Earth or is our solar system or Betelgeuse goes? What's going to happen? Do we have to worry about supernovae?
Probably not. So, in fact, at Rutgers a couple of years ago, I taught a seminar called "Death from the Skies."
Yeah, there's a book by somebody. Who was
we used Phil Plate's book as the textbook for that class for that seminar. And for a supernova, it turns out we're not. Any of the stars nearby that are massive enough that are likely to become a supernova are not near enough to really affect us. A supernova would have to be pretty close, within just a few light years, to pose a serious problem. So, so right now we're not in danger. However, there is evidence on the Earth that there have been nearby supernovae where the Earth and the Sun were just near a massive star at a previous time in the history of our orbit around the galaxy, where that did happen. So, we don't have to worry right now, but maybe in the future it could happen.
So what keeps me up at night are gamma ray bursts, but that's another topic. I would like to. We should have a hangout on that too, Carol. A death from the skies or something. You know, ways in which we can die. Okay, so Charles Bell is asking, and this is a good segue into the next thing I want to talk about on the Google Plus event page. He's asking, is there a pipeline process to check new images taken by Hubble for supernova in any galaxies in the field of view? And let me ask that question another way. How does Hubble discover supernovas? Because the second question is, have any supernovae been discovered by Hubble? The short answer is yes. But maybe Carol, you comment on that a little bit. Some of the ways in which Hubble look at the sky to find supernovae.
Well, also, I think also Saurabh can probably address this as well, but there is a campaign now, ever since, you know, this early work on the expansion of the universe, where there's a number of things. If somebody else discovers a supernova, there are observers that can ask the director to immediately look at that object and take a series of observations with the Hubble Space Telescope. There's also a campaign for observations that are taken by other observers at distant galaxies to comb through that data to look for supernova. So there are other telescopes that look for supernova in particular, and asteroids and all kinds of things. Hubble does not have a campaign specifically where you just point in the sky and hope there's a supernova, but observations that are being used for something else are then examined to see if there are supernova events, and if they find them fast enough, they can go back and observe either with Hubble or another observatory.
So, Rob, do you want to elaborate on that a little?
Yeah, sure. So we often call these supernova searches piggybacking on other people's search. So you might have seen these iconic images from Hubble, like the deep field and the ultra deep field. And the way they take those images is that Hubble has to point at one small patch of the sky for a long time, for hours or days. And so you could do that. You could just point it at for a few days at the same patch of the sky, and then just say, okay, here's my great image. But what the supernova folks like to do is say, hey, why don't you slow down a little bit and spread that time out over a few months? And so instead of observing it all at once, take one image and then come back later, a month later, and then again another month. In the end, after a certain amount of time, you'll have your full data set that you can add together and make your beautiful deep field. But in the meantime, we'll be able to look at each month and say, hey, was there a new object there, a new supernova that went off in between? And so that's what we do. We piggyback on these big surveys like CANDLES and CLASH and now the Frontier fields to use Hubble to find supernovae. And the reason we want Hubble to find supernovae, yes, many people can find them from the ground, and even amateur astronomers find supernovae, which is, I think, a really fascinating part of this science topic. But Hubble is the only thing that can find the really, really distant ones, the ones that are 10 billion light years away. And we want to know what the universe was like all the way back then. And so Hubble is really key at finding the most distant supernovae, and we love to use Hubble to find them.
So I was going to comment, because I think, Tony, you mentioned it before at some point, that in the frontier fields, which are deep observations that are being taken over a 3-year period of 6 clusters, and we've talked about that on Hangouts before, and just as Saurabh said, the observations are interspersed, and also you don't want to dominate just with one program, so other programs are fitting in between this. And very early in the frontier fields, one of the first frontier fields observed, there was a supernova, and it is likely over a 3-year period that those fields, because those observations are spread out for so long, that other supernovae.
Oh, by the way, I wanted to mention one other thing. The question asked whether there was a pipeline to do this, and there is a pipeline, and that pipeline's name is Curtis McCulley, among others, Steve Rodman. So we have people, and Curtis is a graduate student with me at Rutgers, and when he was here, he helped develop a pipeline that's now being used in the frontier fields. When Hubble takes new data, you have to take that new data, match it up with the old data, subtract the 2 images to look for anything new, and often there's a lot of stuff new, a cosmic ray that was in one image that's not in the other. And so Curtis developed some of the tools, some of the software that we use to find what are the real new things, the real new supernovae.
I'm being an evil producer right now and telling Tony to put on headphones to.
Yeah, so I'm doing it now.
Thank you.
Thank you. Okay, you can speak now.
Well, not until I change it.
No? I don't know, we can hear you pretty well.
Is it better?
No, it's worse. What you just did made
you're
it
on. Yeah, your microphone's down, but the echo is gone. So,
yeah.
Which I kind of like. I don't hear you.
Is this better?
No. You're very faint. Put the microphone in front of your mouth.
Speak into the microphone, Tony.
I am speaking into the microphone.
No, the microphone is far away from your mouth.
Is this better?
Yeah.
Yeah.
Okay. All right. Now, sorry about that, folks. I guess I had some feedback. Okay. So I don't know if this is going to work or not, but Elena, if you could put up the Frontier Fields thing on the little new showcase app that they have, hopefully this will be something that will illustrate what we were just talking about. With the question of has Hubble discovered any supernovae? The answer is, of course, it's discovered many, and in fact, with the Frontier Fields initiative, one of the things it does, and one of the ways in which supernova are discovered, is you look at a patch of sky, you take some images, and then you go back and you look at it again, and if there's any new stars, you'll know that, hey, there must be, that's a supernova going there. That's one of the triggers for having seen one. And I think Frontier Fields was going for just a few weeks, and it had already discovered its first supernova. So this one wasn't particularly bright or anything, but it was a discovery. Curtis, I may be off track here with this question, and if I'm asking the wrong person, please let me know. But your organization, LCOGT, do you guys have any supernova surveys, ground-based surveys there?
So LCOGT is actually designed to be more of a follow-up machine, kind of what I'm sorry, Carol was saying earlier about where somebody else discovers a supernova, and then we can simply turn one of our telescopes and start observing it.
Okay, all right. So there are surveys, though, that look at large areas of the sky multiple times a night or multiple times over the course of some period to find these supernovae, in big areas. So, okay, so I want to move on to some of the particulars of some of your work with Hubble. So, Rob, you have mentioned something that you had done something with a zombie star with using Hubble. Do you want to talk about that a little bit?
That's right. Yeah. So actually, all three of us, Ryan and Curtis and I, were working on this kind of object, and we talked about how Type 1a supernovae are so important for cosmology, and yet Ryan said, "Oh, here are two possible ways they might explode. One was with two white dwarfs that merged together to explode, and one was material from a more normal star being dumped onto a white dwarf to explode." And so you would think that, hey, that's a big difference whether you have two white dwarfs merging or not. And yet these are the same objects that you use to measure the accelerating universe. And Carol was asking, doesn't that make you uncomfortable that you don't really know exactly how they explode? And it does. And so apart from the cosmology application of these Type 1As is, what are they? And so for a while we've been trying to attack this question with, lots of people have. And one of the things we like to do, because, I don't know, maybe we're kind of weird people, but we like to look at the weirdo Type 1As. So every so often we get a Type 1A or something that looks like a Type 1A, but isn't the same luminosity. It's somewhat different. So there are a few that are a little too bright, and then there are a few that are too faint. And we've been studying the ones that are too faint. And we still think that these are these dwarf explosions. Ryan came up with a great name for them. We call them Type 1AX supernova, and the X is mysterious, and it also harkens back to the first one that we identified of this class, which was a supernova called 2002 CX. And so the idea is if we can study these weirdos and what makes them different than normal Type 1As, we might understand, aha, all the weirdos come from this kind of star, and all the normals come from two white dwarfs merging, or whatever the case may be. And so we've been studying these weirdos, and one of the things we'd like to do with the weirdos, there was one in 2012 called 2012Z, and it was a great coincidence that galaxy that it went off in NGC 1309. I don't know if we have a picture of that. I think I sent one.
Yeah, do you happen to have that handy?
The before and after of 2012Z. So what we did is there was already, and this is one of the great things about Hubble, is that there's the Hubble archive. So any astronomer, after the Hubble data has been taken, after a period of time, usually a year or so, that data becomes public to the whole world. And anyone can go look to see what is in that data. And so this supernova went off in 2012.
Scott has it up now.
Okay, great. And so that's actually
This is
another
2014
supernova, 2014J, yeah.
Oh, okay.
So we had the supernova in 2012 that went off in this galaxy, NGC 1309. It's a nice, beautiful spiral galaxy, and there's little 2 inset boxes on the link I sent. Anyway, and what had happened is that one of our colleagues had actually taken lots of images of that galaxy to study the aftermath of 2002. So in the Hubble archive, there were these great images of this galaxy, and what we could do is we could go back and look to see what was at the position. There it is. So there's that beautiful galaxy on the left, and then on the right, if we zoom in on the location of the new supernova in 2012, on the right, what we found, and actually this was really due to the work of Curtis, who took all that old data and combined them together in a really optimal way to make all the stars as sharp as possible. So on the lower right, you see the position of the supernova, which went off in 2012. The image is actually from 2013, when the supernova was faint enough that we could get a good image with Hubble. And then on the upper part is the data from 2005 and 2006, before the supernova went off. And what we found for this weirdo white dwarf supernova, this type 1ax that we call, is that there was actually something there, where that arrow S1 points to a little blue smudge. Now, that probably doesn't look like much to the viewers, but when Curtis showed me and Ryan that, we were ecstatic. I'll let them tell you about what their feelings were when we made this discovery. But the idea that for a white dwarf supernova, where people have been looking to see a progenitor, the star that exploded before a white dwarf supernova, for a long time, and they never did, and so that actually led a lot of people to think that most of these white dwarf supernovae came from 2 white dwarfs merging, where the white dwarfs would be too faint to see. That's why we never saw them. But in this case, in this weirdo case, we did see something. And so we wrote a whole paper on it. It was in Nature, and we did a little press release. And I don't know who it was. Maybe Carol had a hand in it. But someone said, we would talk about, well, this is this dead star, this white dwarf, but it sort of got resurrected when it got this material transferred onto it from this blue companion that we're seeing. And so, well, that sounds like a zombie, And so we called it a zombie star, and we went with that. And the news loved that, so there were lots of news articles about this zombie star that we discovered. And really the important thing is that, it was the first time for a white dwarf supernova we got to see what was there before, and we actually saw something.
Great. So we are almost out of time. Boy, this has gone by fast. I had a lot more.
I just want to point out that one astronomy that has not changed since the first person who called him or herself an astronomer looked up and named a star is that we name things any which way we want. And that's why we have lots of weird names of objects.
I always thought it was the zombie star because I'm seeing these supernova remnants and they kind of look like brains. And I just, like, oh, I see why they're zombie stars. They're just
I think you see what you want to see in them. I think they're a little like Rorschach tests, so maybe it's telling you more about you and zombies.
Well, honestly, I think they look like Metroids, but that's just like the old school gamer in me.
Oh my goodness.
Okay, so let's get to one question before we have to go. This is from the Q&A app. Shane Taylor is asking, may the variation of brightness between type 1a supernovae be the difference between what type of stars cause it? A white dwarf type 1a supernova throws off a specific type of brightness compared to a type 1a triggered supernova by a merging of 2 neutron stars. So let me parse that a little bit. May the variation in brightness between the first of all, is there much of a variation in brightness between the different types of type 1a supernovae? They're pretty much all the same. That's the point, right?
So I'll handle this because I've done a little bit of work on this. So first of all, for 1As, we don't know what creates them. We don't know if it's the merger of 2 white dwarfs. The question, says neutron stars, but we know it's not that. It could be the merger of 2 white dwarfs, or it could be this white dwarf that gets material from another star. And we don't know. It could be one or the other, or some combination of both. The one observation that we have that shows some difference between progenitor systems, and this is not in terms of the the companion stars necessarily, but we're able to detect if there's outflowing material in the circumstellar system. So we can figure out if there's some sort of wind coming off of either an accretion disk or the companion star or something like that. And we can say that some stars seem to have that and some do not. Some, stars that end up becoming type 1a supernovae. And if you separate those two classes, those that have these outflows and those that don't, their luminosities, we still have not been able to say that they're different, but we can say that the velocity at which the material is expelled is slightly different for those two systems. But that's the only observation yet that we have for the progenitor systems themselves. Now, we have made other comparisons at sort of like bulk properties of the galaxy. So we know, for instance, type 1a supernovae that come from big elliptical galaxies, they tend to be fainter intrinsically than the ones that come from spiral galaxies. But we correct for that because of this light curve thing that Saurabh was talking about before. And if you make that correction, then there's no difference.
It's a great question because that's exactly what you would think. The different progenitors should lead to different kinds of supernovae, even slightly different. Maybe the two white dwarfs would be slightly brighter or fainter. And so the question that the questioner asked, I mean, that's exactly the kind of hypotheses that as scientists we kind of formulated. And we're like, okay, let's kind of look and let's see if we can tell the difference in the brightness if they come from this kind of galaxy or if they're really young or they're really old or something like that. And the really surprising thing is that the 1As are very similar. There is some range, but it seems to be somehow nature, no matter what the inputs were. A writer used a great analogy, Nadia Drake, in an article that she wrote about type 1A supernovae. It's like you have different ingredients and different recipe, and yet the final product turns out the same. So somehow nature does that, and we're trying to figure out why that is.
Wow, that's a great analogy. Okay, well, thank you, Shane, for that great question. I'm afraid we're out of time, folks. We're going to have to stop here. I want to thank you guys, Saurabh and Ryan and Curtis. This has been an awesome hangout. Thank you for taking time out to talk about supernovae with us. And next week, folks, we'll be back on our regular time on Thursday, 3 p.m. Eastern, 7 p.m. Greenwich time, where we will be talking about the plumes of Europa. You may remember recently that we did a press release where there were some research done looking at Europa plumes, and so we'll have the scientists on hand to discuss that. So we'll hope you'll join us. I'll have the event up by tomorrow, so you guys can let us know you're coming. On behalf of Carol Christian and Scott Lewis, my name is Tony Darnell. Thank you all for watching.
Thanks.
As always,
Thank you.
Keep looking up.
Keep looking up, yeah.
Keep looking up.
also, we're noticing that there is a new thing on the Google Hangouts on Air interface. There's a little pair of hands where you can, I guess, do something, applaud or something like that. So feel free to use that and do whatever that thing does. I don't know what it is yet. We're going to be experimenting with this thing called a showcase where we're going to try and show you some new things during the Hangout as well. All of that will be a little bit experimental. So let's get on with it. Supernovae explosions. That's what we're here to talk about today, and they are among some of the brightest events that occur in the universe. They are these deaths of stars that are, for a brief period of time, can outshine an entire galaxy. In fact, they will put out more energy in a few weeks and a few months than the sun will in its entire lifetime. So these are very energetic events. They occur at a rate which we will talk about a little bit later on. I don't want to give away too many punchlines because I just want to give some background on the kinds of things we're talking about. Not all stars blow up. Only certain ones do. There's also different types of stars that are explosions that can happen. And to talk about all of these details today, we have a panel of expert astronomers. And let me introduce them first. From Rutgers, an astronomer, Saurabh, is it Ja?
Ja, yep.
Oh, great. Oh, man, I love that when I don't screw it up too bad. He's an astronomer at Rutgers University. Also with us is Ryan Foley, a professor at the of astronomy at the University of Illinois, a place where I spent a couple of years, so it's nice to see somebody from U of I there. Also, Curtis McCulley, he's a postdoc at, you just say it. Where are you from, Curtis?
So I'm at LCOGT and UCSB. So LCOGT is Las Cumbres Global Telescope, and UCSB is University of California.
Hello, everybody, and welcome to our latest Hubble Hangout. We are back from our 2-week summer break. Thank you guys for watching today. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today we have a really great hangout planned for you today. Today we have a hangout planned today. Okay, so I'm going to be redundant also. But today we're going to be talking about...
today?
What?
Sounds like you planned it today.
It's today. It's today.
No, I didn't. It's tomorrow. Okay.
All right, let's get into
today's topic is we are going to threw off my groove there. So today's topic, we're going to be talking about supernovae, what they are, the basics of them, and some of the latest research with supernova explosions. We have a panel of astronomers here to help us with that. Joining me this week, as they always do, is Dr. Carol Christian. She's from the Space Telescope Science Institute. Also, welcome, Carol. Did you have a good vacation? Did you have a good time off?
Absolutely.
Yeah. Okay. Also, is Scott Lewis from KnowTheCosmos.com, and he's all over the place in the internet, doing all kinds of awesome things. Welcome back, Scott. It's good to see you again.
Yes, good to see you too. Okay. I've missed you.
Yes, I've missed you too. Yeah.
I haven't missed you guys at all.
I've missed you, Carol.
Oh.
I don't care what you say. I've missed you.
Okay.
I just need to aim better. I'm getting rusty.
Okay.
So, like I said, today we are going to be talking about supernovae, and we want you to interact with us. And the way you can do that is Hubble Hangout hashtag on Twitter, the Q&A app on YouTube, and Google Plus, and the Google Plus event page. We hope you'll leave us questions and comments.
So we can see now the guts.
Scott's got it up now.
That exploded in 1054. So almost 1,000 years later, we can see what it looks like. So it's pretty amazing.
And this would have been something people could have. Well, obviously they did look up and see it in their own night sky. And I believe they're saying it was bright enough to be seen during the day. Is that correct?
Yeah, I think that is true. Yeah, and it's in the constellation of Taurus, I think. And usually at that time, new stars in the skies, that was usually bad for the king or the emperor or whatever. That was usually a bad omen. But for us in astronomy, we love to see stars explode and see what they're made of, and see them enrich the universe with all that stuff.
Yeah, comets have that same reputation. So, all right. So supernova explosions are a way in which a star can die. Now, most people know, and if you don't, I'll remind you that stars burn through nuclear fusion. They have these gases that let them shine, and it's very complicated, and they generate a lot of energy. But stars also come in different shapes and sizes and colors and temperatures. What kind of stars end their life this way? Let me get Ryan in on this. How about, can you take that one for me? Oh, you're muted, I think.
Sorry.
There you go.
So first of all, what we think is just about every star that's particularly massive, say something that's 10 times as massive as our sun or even more, will probably explode as a supernova. There's some actually really interesting theoretical ideas that maybe some subset will collapse directly to a black hole and not have a supernova at the end of its life, but the vast majority should. And we've seen this because we've been able to detect stars after we've seen the explosion. We've gone back at our
Santa Barbara.
Okay. Thank you, and welcome to all three of you. So let me start with you, Rob. Can you give us some background, some basics on what supernovae explosions are? What are they?
So that's great. And supernovae are exploding stars. So we have this word, and even the word sometimes trips people up. So we usually say one is a supernova with just an A at the end. And if you are talking about more than one, then that's supernovae with the AE. It's this funny Greek-Latin hybrid thing. So the New York Times calls them supernovas. So feel free to call them supernovas as well. That's totally fine.
No, supernovae.
We can't? Oh, okay.
Yeah.
Sorry, New York Times.
You have to say supernovae because it's fun.
All right. Yeah, so they're exploding stars, and as you said, right at the end of their lives, some stars explode, and I guess we'll get into which ones do. And there are many different kinds, and we're trying to figure out what kind of stars turn into what kind of explosions, and the Hubble Space Telescope has helped a lot with that.
Now, we know a lot about supernovae already. I mean, we've been seeing them for thousands of years. I think the first recorded supernova, as we're always taught in Astronomy 101, was in 1054, right?
Yeah, there may be some records even before that, but yeah, 1054, we have a pretty well-documented one, and you can go back and look at records that people kept in China and Japan saying in fact, on July 4th, 1054, before the fireworks that were used to. Yeah, absolutely, but there were some celestial fireworks that day.
I don't think that's a plug for America, though. Just
yeah.
America.
It was a premonition of great things to come in America. Yeah, and then actually, what the amazing thing is now we can go back and the astronomers at that time kept really good records of where that new star occurred, and we can go back and look at that right now. And when we go there, we point, for instance, Hubble there are beautiful images of the Crab Nebula.
Old images and seeing the stars there, and then we see the supernova, and then we look much later and we see that the star is gone. So we know that that's happened. Then there are less massive stars that eventually, after going through this full process of living their lives, kind of like our sun, and going on to another stage called like the red giant stage, where they're really big and puffy, and then eventually becoming a white dwarf. A white dwarf is essentially just the center of that star after all of the nuclear fusion has happened, and it's just slowly cooling down. But a subset of white dwarfs that are in systems with another star very nearby can gain some mass from that other star and eventually get to conditions inside the star where you can restart nuclear fusion, but you restart it in a way where the nuclear reaction is a runaway. It causes a major explosion, and that will result in a supernova. So those are the two main categories of stellar explosions.
And the big factor here that determines whether a star explodes or not is its size. I think you said 10 times the mass of our sun, right?
Yeah. So there's one of the very important areas of research right now is determining the exact minimum mass, the smallest a star can be and explode in that way. And most people kind of are pinning it around 8 times the mass of the sun. But 10, we will see that thing explode for the most part. But yeah, and it's actually the mass of the core near the end of its life, not necessarily how much how big the star is when it's more like the sun when it's burning hydrogen into helium. It's really at the end that matters. But that's a technicality. For the most part, we can if it starts off at 10 times, it'll explode.